Last time in the last session, we concluded our unit number 3, which is about RTOS, and we'll just revise what we studied in the last lecture. We'll start with the fourth unit. Okay, fourth unit is about embedded system design. Okay, it's all about design and standard practices and stuff like that. Okay, so that is interesting bit in embedded system. Okay. So during last lecture, we studied IPC and synchronization in RTOS. Okay. So what is IPC and what is synchronization? IPC is basically inter-process communication. Okay. And synchronization is different than this. Okay. We cannot use these terms interchangeably. Okay. Means that IPC is exchanging the message for the purpose of synchronization. Okay. But synchronization does not mean communication. Okay, synchronization means suppose there is a resource that is needed by multiple process or multiple objects at the same time, then who gets to access it first, at who and how, okay, is nothing but synchronization. And who makes it possible? In the process, communication, that is what is making it possible, okay, for tasks to communicate among between each other and decide like what to do and how it is supposed to execute. This is IPC and this is synchronization. Okay, so there are some mechanisms for IPC, okay, that we had studied in detail in the last lecture. So those are message queues, semaphores. Message queues are nothing but buffers. Okay, buffer is nothing but the data is latched into the buffer for communication purpose. Okay, and then that is exchanged on trigger of an event or something like that. Okay, and a task can send, means a task can push a message to a queue. Okay, and get a message out of queue as a, I mean, when it is receiving. Okay, so it's basically FIFO, first in first out queue. Okay, this is because this is a queue data structure. Okay, then a semaphore is basically nothing but a signaling mechanism. Okay, signaling mechanism, it's of mostly two types. एक बाइनरी सीमाफोर होता है, एक काउंटिंग सीमाफोर होता है. Okay, binary and counting. So both of them works differently. Binary is only having 0 and 1 value. Okay. So when a task is available, when the resource is available for task to consume, semaphore is 1. Okay. And when it is busy, okay, when the resource is engaged, okay, it is 0. So this is the signaling mechanism. Okay, used for synchronization. Then similarly, we have mutexes. It is also a semaphore only. It is a special kind of semaphore. Okay, and it also makes sure that only one task is getting to use the resource. Okay, then then there are event flags. Okay, these flags are a way for tasks to signal each other about the occurrences of specific event. Okay, so it is again for synchronization purpose, but this is an IPC mechanism. Okay, we have mailboxes, there are pipes. Sorry. So mailbox is similar to a message queue. Okay, but more complex structure than that. Okay, it allows messages or data to be pass between the tasks, often used for handling the structured data in more controlled manner. Okay, structured data. Okay, it needs data to be in particular format. Okay, it needs data in particular format. That's what it needs, structured data. And pipes are unidirectional data system used for communication between tasks. Okay, data returned to pipe by one task can be read by other. Okay, so pipe is again, take it as a queue, but it is unidirectional. Okay, only either it can be pushed upwards. Okay, but the thing is that suppose task A has pushed data into it, task B gets to read it as well. Okay, task B can do the reading part. So it's that. Then we have shared memory and signals as last two IPC mechanisms, and these are like shared memory is uh, multiple resources or multiple tasks sharing the same sort of memory. Okay, memory means RAM. Okay, of course. Hmm. So if they are sharing the same memory, of course they have access to it and they can read what is going on in it. Okay, so this mechanism is, multiple tasks access the common region of memory. It allows efficient data sharing during, the data transfer or during the synchronization process. Okay, the data sharing would require synchronization to avoid the conflict. Okay, so synchronization is needed. Okay, if we this is an IPC mechanism only, but to have this mechanism implemented, synchronization is needed. Okay, or else what will happen? Why synchronization is needed? Because RAM is a resource. Okay, RAM is already a resource, and I'm saying several tasks are sharing this resource. Okay, means they need to access it, and if they run and try and access that region of memory at the same time, then that is a race condition. Okay, and to avoid that, there should be synchronization. There should be some semaphore working on it to avoid this situation. Okay, is signal then. Signals are used for inter-task communication by notifying one task of a specific event or a condition. Okay, so it's again, as the word says, it's just a signal. Okay, it just informs the task about the condition that is gonna occur. Okay, and that's how synchronization is achieved using signals. Then we have ISR and conditional variables. Okay, ISR, you guys know already. Conditional variable are synchronization tools used in situation where one task needs to wait for another to signal the occurrence of an event. Okay, so this is a wait and hold mechanism. Okay, wait or hold mechanism. Okay, in this state of task changes. Okay, based on the condition, variable. So variable are synchronization tools. Okay, in which situations where one task needs to wait for another to signal the occurrence of an event. Okay, means suppose T1 is executing at the moment. Okay, then T2 will wait on its own for some event to occur. Okay, and that event will act as a trigger point for T2. Okay, suppose सपोज T1 टास्क में टेम्परेचर सेंसर से डेटा रीड हो रहा है एंड कन्वर्ट भी हो रहा है, ठीक है, डेटा टू रीडेबल वैल्यू, देन an event could be about generation of a value, and this could act as a trigger point for T2, and the T2 it could be about displaying the data on the LCD, and then it will trigger and it will display, it will do its work. Okay. Then we started with heap memory management. We first of all started why heap. What is heap memory? Okay, it's mostly the memory that we use for dynamic allocation. Okay, dynamic memory allocation. So both static and dynamic has its own advantages and disadvantages. Okay, so in RTOS, basically, okay, we are going to look at the commands which are specific to free RTOS. Okay, free RTOS is a RTOS, one of the RTOS's distribution. Okay, so we're going to look at free RTOS. So in free RTOS, if we got to use the static memory allocation, we should there is this free RTOS config.h header file. Okay, and we should be having this config support static allocation set to 1, okay, in this header file. uh, and if we want to use dynamic memory, then we have to, I mean, if we want to allocate the memory dynamically, then we definitely need to do config support static dynamic allocation set to 1. Okay, and it is also valid to have both of them set to 1. Okay, that is not a problem. So there's one thing. Next thing is that why not dynamic or why not static? I mean, why not any particular thing? So static memory allocation and dynamic memory allocation. In dynamic, the basically the memory block of memory is getting allocated at runtime. Okay, and static में compile time करता है. Okay, so the thing is that in static we know, okay, how much of it we gonna need. In dynamic होता क्या है, we are not sure about it. Okay, we are not sure. Plus there are some fragmentation losses in dynamic memory allocation. Fragmentation loss क्या है, डिटेल में देखा था हमने. यहाँ पे मेमोरी ब्लॉक, यहाँ पे भी बिजी है, लेकिन बीच बीच की स्पेस जो बचती, दैट इज कॉल्ड फ्रैगमेंट्स. ओके, so this happens in the dynamic memory allocation. Okay, then how do we use it? It's mentioned detail. Okay, and enabling static memory allocation, there are some commands that are there. You can go through them. Then we started with different RTOS examples. Okay, and selection criterion. Okay, selection. So primarily, most widely used RTOSs are this free RTOS. Then we've got VX works, again very popular. Then we have QNX. So free RTOSs में we have kernel which comes with preemptive and cooperative scheduling and task management and the inter-task communication. So in memory we have static memory allocation support, no dynamic allocation support by default. Means you've got to change that variable and you have to set it 1 in the header file explicitly. Okay, no support by default. Okay, then it supports multiple tasks with priorities. Okay, task synchronization and inter-task communication. Okay, portability. Okay, it supports a wide variety of microcontroller architecture and tools. It has small footprint. Okay, designed for a small with minimal overhead. Okay, making it ideal for resource constrained devices. Okay, resource constrained application only can run good in free RTOS. Okay, there are several reasons to it. It is no GUI networking support, one thing, and plus one more is multi-core operations के लिए ये proper नहीं है operating system. Okay. built-in support to multi-core. See, multi-core process can be manually adapted anyways. So then we have VxWorks. So VxWorks is, of course, we need money for this. As in FreeRTOS, it was already free, okay, but we have to have a subscription for VxWorks, okay. It does give networking support and the multi-core support, and plus the other features that FreeRTOS had, okay. And in addition to that, we have these two features. Then the cons is it's commercial licensing. Okay, like it means that it can be expensive for some use cases. Okay, so we have to select it accordingly. Okay, can be more complex to learn and use compared to simpler RTOS operations like free RTOS. Okay, more overhead than simpler systems. Okay, which may not be necessarily for small reduced resource constrained applications. So these are. Then we have QNX, of course. Okay, the QNX was developed by BlackBerry. Okay, it also gives you networking and multi-core supports, but it is again commercial proprietary license. Okay, so we got to license it. Then selection criteria we studied. Okay, in selection we talked about project. We started with project complexity and safety and reliability. Okay, so if project is small and resource constraint, FreeRTOS is an excellent choice. Then for larger, more complex system, multi-core processors, networking, and safety requirements, VxWorks or QNX may be better suited. Okay, then safety and reliability for applications requiring high reliability or meeting industry safety standards, example automotive, aerospace, industrial control, VxWorks and QNX offer specialized support. Okay, FreeRTOS does not have built-in safety certifications but can be adapted for simpler non-critical applications. Okay, then if we consider budget and licensing, then if cost is concerned, you are looking for a free open source option. FreeRTOS is the clear winner. Okay, VxWorks and QNX are commercial products with licensing cost. Okay, but they offer extensive features for large scale or mission critical systems. So if you have budget, okay, and if you also have an application that needs complex, network or multi-core support, then this is for you. Okay, QNX and VxWorks. Okay, then hardware requirement. Okay, FreeRTOS deal with a ideal for small low power microcontrollers with limited resources. VxWorks and QNX are better suited for systems that are multi-core processors. Okay, high performance networking and advanced memory management. Then development tools and ecosystem. And VxWorks and QNX both come with robust development tools, IDs, debuggers, safety certification tools, and blah blah blah. And they're essential for enterprise level development, because in enterprise we have this compliance thing going on, and for this achieving this compliance we need to have all the essential IDs, debuggers, safety certification tools in place in order to get this done right. Okay, so this is one thing. Then yeah, this is where we ended with the arts. Just wanted to give you an overview. Now we'll start with our fourth unit, which is about the embedded system designs. Okay. What can you see, Shubham, on my screen right now? Hey, Shubham, you there? Anyways,
Yes, sir.
what can you see? What is
Whiteboard.
okay? Okay. This is our unit number 4. Okay. Very interesting and easy going. Okay. So in embedded system design and development, so the this unit basically deals with what are basically the standard practices that are followed during the design. Okay, a little bit of history into design industry, then standard practices, then protocols and design methodologies. Okay, then we gonna see testing and it embedded testing. Okay, because our stuff is gonna be there in this unit. We also we have simulators for embedded simulators IDE. Okay, we are already using one. Okay, simulator and IDE, but we gonna officially study it in this unit. Okay, then we have like power management systems we're gonna learn here. Okay, then we're gonna learn the low power design. Okay, similar stuff like everything related to designing a system. Okay, so let's start with like our design process. Okay, so design process is nothing but uh, you know the steps we take, the sequence of steps we take to build a product. Okay, and the main goal of the design process is to create the product that does something useful. Okay, so product, what is product? Product is something that is this is a product. Okay, and why is this product there in market? Because it has some purpose. Okay, it has some purpose, it's doing some work, it's doing some meaningful work. Okay, it is nothing but the product. Okay, and the process that we used, the steps, the sequential process that we used to design it, the steps that we took is nothing but the design process of the product. Okay, so the important goal of design process are to adherence to the functionality and performance and power requirements of the system. Okay, so there are n number of things if we talk about design. Okay, but embedded industry, these three things are giving value, which is time to market, then we have design cost, then we have quality. Okay, these three things are given extreme importance. Okay, so time to market means basically from conception of the product to the time it took to come in the market for sale purpose. Okay, from conception to actual sale is nothing but time to market, and this matters a lot in embedded industry because there is a huge competition. Okay, competitors are huge. Okay, if you're saying I'll deliver it in like 3 months, there will be other company delivering it in like 2 months. Okay, and while doing this, we cannot forget the design cost. Okay, so design cost is something that you spend. Okay, design cost is something that you spend initially, and then the product cost is decided. Okay, the cost of product is depending on that. Okay, so why should this be considered? Okay, because say you are spending x amount on your product manufacturing. Okay, during the process, design process, so you will charge x plus y from the consumer. Okay, definitely. And if our x factor itself is huge, then how much can we take here? How much is our income? No, it becomes less. Okay, so main thing is that you should try and minimize the design cost. Okay, in order to earn profit from the system. Plus, nobody is going to buy a costly system in the market. Okay, so आप लोग भी क्या करते हो market में? When you go and buy some electronics, you look for cheaper options, and there is a huge electronics market, and you always get a cheaper choice. Okay, if this product is costing you X, next shop will give you X minus some amount, and then you will get it at Z price. So it's always that. Then there is quality also. Okay, so it should not happen. It's electronics, right? It should not happen that you take product home, you run it once, and then it stops working. Okay, you can't do that. You have charged some amount to that consumer. Okay, for selling the product, you should offer the quality that the price deserves. Okay, so that's the quality thing. Okay, so basically we have to deliver quality product in less price and in less amount of time. This is our goal here, okay? Less amount of time, less spending, less amount of time, and quality product. These are our goals basically in embedded design, okay? As a design engineer. Then we're gonna start with okay. So the first model proposed for software development process was what? Waterfall model, right? So we are gonna talk about it. Okay, so waterfall model. So, a design flow is a sequence of steps that are, followed during the design. We already know that word itself is self-explanatory, like design flow means the steps we follow during the design. Okay, some of the steps can be performed by tools, right? Okay, ready-made tools, and some we have to perform by our hands. Okay, manually. Okay, although top-down design is ideal, since it implies good knowledge of the implementation during early design phases. Most designs are clearly not quite so top-down approach. So you know most project designs entail experimentation and changes they require and they require definitely bottom up feedback also. So as a result waterfall model is not so relatable in today's world. So but still this we refer as a base, okay, in any software development life cycle thing. So you must be familiar about it. So in a requirement gathering phase, we which basically do research, okay, research, and we if we have a client, then we get the requirement sheets, okay, requirement sheets, and the sheets should be a detailed document, okay, detailed doc, and it has what details? It has the specifications, okay, then functional and security requirements, okay, all the details that you need to design the system are gathered over here, okay. Then we define an architecture, okay. Then the system is already actually is designed here, okay, depending on the things that we know about it, okay. Means architecture phase, then starts the coding part of it, then the testing, and then maintenance, okay. But what is happening in this approach? Okay, this approach is like this, okay. Top down approach, okay. We start from here and end here, okay. And thorough knowledge of the system is needed in order to develop any system with this approach, okay. If we develop it using a dynamic approach or as we go approach, then these things are not applicable, okay. Like but such a waterfall model is very a traditional model, okay, because systems nowadays are not so top to top bottom approach, okay. Most of the systems are bottom up feedback wale systems होते हैं, right? So Okay, and that's why this model is quite irrelevant. Okay, and not not really referred as the model of software. The current model of software development. So this though this is irrelevant, we need to know basically what are the steps in designing a software, okay, or a system to be talk on general terms. You must have studied the waterfall model, right, Shubham?
Yes, sir.
Yeah, so वही चीज है ये वे relevant नहीं है फिर भी as a history we got to take a look at it and then just study it really. So this is how it is. Then comes the spiral model. Have you heard about the spiral model, Shubham?
No, sir.
The spiral model is something like, the see, waterfall model implies, the system is implemented only once. Okay. In waterfall model, system is built only once. In spiral, होता क्या है कि we build the system multiple times. Okay, during multiple phases, okay, of its design, during multiple phases of its design. Okay, so in
Yes, sir.
spiral, basically, see, every phase, suppose there is requirement gathering, then there is architecture, then there is coding, there is testing. Okay, it could be anything. Okay, it could be anything, but or maybe it could be specification wali phase. Okay, it could be maybe prototyping. You have mobility to define your stages. But then there is initial system. Okay, then you have enhanced system. Shit. Initial system. Then you have enhanced system. Okay, and at each step. Okay, and at each step you have we are what we are doing at each step is requirement test and design. Okay, at every single step. Okay, at every single step we are doing requirement design टेस्ट ओके सो देखो इस स्पेसिफिकेशन के फेज में हमने ये तीन चीज करी फिर प्रोटोटाइपिंग में भी करा इनिशियल सिस्टम जो डिजाइन हुई उसमें भी ये किया हमने एनहांस सिस्टम बनी उसमें तो ऑफ कोर्स करना पड़ा ओके so this is the spiral design okay means we design the system multiple number of times okay design the system multiple times okay so the benefit of this system is that we get to know the system better way okay we get to know the system much better way okay because we are doing it multiple times right there are multiple times that we are designing the system okay and this is Basically, the methodology followed during the design is successive refinement. Okay, so successive refinement will come to it. Okay, means we are refining our system in successive set of process. So this is nothing but successive refinement. In every phase, we are refining our system and we are enhancing it. Okay, so this is what successive refinement. Basically, like suppose there are few stages in your design, like specify, then architect, then design, build, and test. So uh, these are process mostly followed, right? So in the initial system, these things are done. Again, refined system, similar things are done. Again, some other phase, same flow is followed. So similar flow is followed during the each phase of the design is nothing but successive refinement. So one more important thing to talk about over here is that even though this is best, this sounds good now to see, like it looks good to us, like, oh, I have a system that has been designed multiple times, and developers or the team knows about the system, the very best possible way out there is, we think about it, but such things are really complex, right? It is very complex, it is time taking. Okay, even though better support is possible here, but it's still time taking. Okay, so this is how it is. So this is the spiral model. Okay, then let's actually talk about how it happens when hardware plus software is equal to most of the embedded systems. I'm not saying all, most of the embedded systems. So how does it work? We'll see. But before that, let's go on a short break, okay, and be back in time. Hey, you were able to see my screen, right?
Yes, sir.
Okay, okay. Now what are you seeing?
Yours, sir. Your
You don't see my screen, right?
no, sir.
Okay, that's because I stopped sharing.
Yes, sir.
Okay. So go on a break and be back.
Okay,
Wait,
sir.
10 minutes का break है.
Yes, sir.
Hi Shubham, you there?
Yes, sir.
Okay, then let's resume. मैं दिख रहा हूँ या नहीं?
Yes, sir.
So मुझे बताना जब तुम्हें स्क्रीन दिखे। दिख रही है स्क्रीन?
Yes, sir.
ओके। So so far we've studied like how like waterfall model and spiral model works. Okay. Okay. So spiral is more complicated but best. Waterfall is just ideal, okay, but not relevant anymore. So that is the thing with these two models. And now something that we're going to study right now is the combined approach of hardware and software design, how it is actually taken forward. I mean, developing both the systems in parallel and then combining it or testing. How does it really work? So let's see that. So requirement and specifications. Okay, requirement and specifications. Okay, this is the first phase. Okay, in this phase, what happens is that requirement and specifications are gathered. So requirement is basically what is requirement. Requirement is informal communication between client and the company who's designing the system. So requirement is the informal communication that tells what client want, okay, what is customer wanting actually, and specification is the detailed representation of that. Okay, so requirement and specification, this is how they are related. So this is requirement and specification. Okay, fine. So after this, what happens once you have requirement, once you have specification, the specification sheet will have the features that you should have, you must have, and you can omit. Okay. So there are options that comes on the specification sheet. Okay, which I mean, in system, which features are must to have. Its features are. It's okay if we avoid those features. Okay, such things you will find under the specification sheet. Then there is architecture phase. Okay, architecture phase, in which we put down the whole system in a tool or on a paper. Okay, we design how we want our system to be. Suppose it is a simple uh, temperature detection. Okay, temperature detection, that's it. Then आर्किटेक्चर में कैसे आएगा कि which sensor, where the sensor will be deployed, which microcontroller will be used, where will it be placed, okay, what software will be there, okay, everything will be designed in architecture phase. Okay, and then the design actually splits, okay, the hardware part and the software part. Okay, now there is hardware and there is software. In hardware, we need to we need to have a microcontroller, we need to design a board in which all the components are placed. Okay, we need to get it done by somebody, we need to do it ourselves, it's your choice. Okay, you might have any enclosure box for this system, everything, every aspect of hardware will be taken care. Now again, in hardware design, again there will be huge number of steps that are followed. Okay, selection criteria of each and every component on this board. Okay, then security point of view. Okay, tampering point of view, everything should be thought of in the hardware design. Okay, the enclosure should be strong enough, attractive enough, lightweight enough, portable enough, mobile enough if that is required. Okay, everything right from the circuit to the enclosure, everything in hardware is taken care, and the software the similar way. Okay, coding. Okay, coding, then checking it for errors, testing it, then security point of view, everything you have to uh, do. Okay, individually, independently. Okay, then another phase comes, which is integration. इंटीग्रेशन में क्या होगा, सॉफ्टवेयर एंड हार्डवेयर को हमने इंडिविजुअली इंडिपेंडेंटली डेवलप किया था. ओके, सो now integration phase is something that will, sorry, combine them. Okay, in integration phase it will be combined. Okay, and then there will be testing in the end. Okay, and this testing will be combined. Okay, so the catch here is that you see hardware design and software design, these two phases itself are, a huge design process, a huge design flow comes if you split this phase and this phase. Okay, so but this is the embedded system design overall. So we gather the requirement and specification, then we derive an architecture out of it, then we have hardware and software design teams working independently of each other on each part of the design. Okay, and then we have combined them, we have integrated them, maybe with like whatever the method is, and then we have done the combined testing of the system. Okay, so this is how embedded system design roughly works. But the main thing here is that these could be like done by, I mean, this is basically done by multiple teams, right? It's not a work of single team, because you see hardware design is there, software design is there. In hardware design itself, we know we have multiple teams. If the system is network connected, then we have certain protocols to be taken care of, and certain things comes into the picture. There are networking guy involved, there is compliance guy involved, there is developer involved, there is hardware person involved, there is electronics guy involved, there is IT guy involved. There are a lot of people involved. Okay, and this all team function together in order to achieve a common goal. And then there is cross functional teams are needed. Okay, there's communication, robust communication requirement is there, because designing a system and the parameters I told you earlier, like time to market, then what else was there, cost was there, right? Time to market, cost, such parameters also should be thought of in order to get the system delivered and deployed. So majority these are the steps in design. But if we, I mean, go on, a proper representation of all the modules, then it will somehow look like this. Okay, so this is hardware design and this is software design. Okay, so as you can see, and this is the overall system. So the software design, again came the specification. See, overall requirement and specification. Hardware में भी specification फिर से आ गया. Okay, then in overall system design we had studied architecture is the next step. And in individual hardware and software phase we follow the same things. Okay, this is again some sort of refinement. Okay, refinement. So then we in hardware system we are checking out for hardware, in software we are checking out for software architecture. Okay, we are designing an architecture there. Okay, then comes the detailed design part. This is where the actual design happens. Okay, another design cycle may be could become could be coming over here. Then there is least abstract and other algorithms could be used. There could be hardware abstraction layers attached and stuff like that could be done here at this point in time, and this is the actual phase. Okay, then comes the integration, and you appreciate how the phases are done individually and combiningly. Okay, so the software part and the hardware. See, the hardware design part is split. Okay, hardware design part is split like this, and software design part is split like this. So like I told you, every module is again split into another set of design mechanisms. So this is how it is. And then comes the integration and test. So integration and testing. Sorry, I've taken medicines. So integration and testing happens individually. Okay, in hardware testing model and software in both, we do the integration, and testing thing. So this is done individually, plus where it is combined. Okay, hardware plus software is combined over here, and then this is nothing but integration, and then main system testing happens. Okay, so basically this is how the whole design thing works. Okay, so the front end activities such as specifications and architect, and simultaneously considering hardware and software aspects. So these activities can be carried out simultaneously. Hardware and software is involved. So backend integration and testing can consider the entire system. Okay, in the middle, however, development of hardware and software component can go on relatively independently. So then it says that once we are done with the common activities, then the team can split up. Then hardware team can work on the hardware, and the software team can be working on the software part of it. Okay, while the testing of one will require stubs of the other, most of the hardware and software work can proceed relatively independently. Okay, it says again that the work can be done independently. You do not have any dependency on it. Okay, then in fact many complex embedded systems are themselves built for smaller design. So it's like many designs may be built for smaller design, so the activities can be carried out independently, independent of each other, and this way it works the best. So this is how it happens. So have you Shubham, ever worked on the hardware part? Ever hardware design you guys have done? Never, I guess, right?
No, sir.
So हम लोग अभी टूल यूज कर रहे हैं ना, कील. Kill for coding, and Pratis for simulation. Okay, so तुमने PCB layout वगैरह कभी सुना है? At least you must have heard these terms, right? PCB layout मतलब अगर कोई सर्किट डायग्राम है, ठीक है, if there are certain components connected. Okay, so ये जो सर्किट डायग्राम हो गई, ओके, एंड प्रोटिस्ट पे मैंने ये बनाई, ठीक है। तो प्रोटिस्ट में ना एक्चुअली साइजेस भी कंसीडर होते हैं। अभी मैंने रजिस्टर मेरे सर्किट डायग्राम में है, तो उसकी साइज भी आ जाती है उधर एक्चुअली। उसके बाद मैंने एक एलईडी कनेक्ट किया है, कौन से टाइप का किया है, मॉडल कौन सा है, वी कैन एंटर ऑल द डिटेल्स, ओके। क्यों, लेकिन व्हाई, बिकॉज Proteus is again a PCB designing software, so it will give you layout also, okay। Proteus में तुम PCB डिजाइन देखोगे ना, तो वो ऐसे कुछ तो दिखेगी तुम्हें, okay। This is hardware design part, okay। Grounding could be just a common connection, okay। So ये हो गई इसकी PCB layout, ये छोटे से सर्किट की, ठीक है। मतलब ये तुम्हें बोर्ड के पीछे दिखेगा, ठीक है। ये जो डॉट्स मैंने क्रिएट किए, ये तुम्हारा पीसीबी बोर्ड है, इसके पीछे ये तुम्हें दिखेगा। ऊपर के साइड में यू विल फाइंड दिस रजिस्टर एंड दिस एलईडी, ओके, कनेक्टेड हियर, एंड दीज आर द कनेक्टिंग लाइंस। सो ये पीसीबी लेआउट है। ऐसे सर्किट में तुमने देखा होगा, है ना, ऐसे ट्रैक बने हुए होते हैं। सो वो who does that, okay, there are some tools available to do that, okay, to make this possible, okay। We draw a basic circuit, we insert components, okay, according to sizes and specifications and everything, and then the structure like this is developed, and this is we print it on a PCB, and then we put solder the hardware on it. So the hardware design is very complex, so that's all I meant to tell you here. So this is being taken care in hardware. Similarly, software part, again, software design part is again entirely different mechanism. Nowadays we are following the agile method, okay, in order to follow the timelines, in order to split the product development into parts and have the traction better way possible, okay। So ये हम आजकल कर रहे हैं, ठीक है। Even hardware design has enhanced drastically during last few years, okay। Software तो है ही, definitely software में भी there are, you know, now software development, at least how many teams are involved in order to develop one software. So imagine a system, embedded system is going to be designing, it's in process of design, and how many teams will be involved in software development as well, because a lot of things comes together when a system has to be designed. A networking guy, a protocol guy, there is a testing guy, there is a compliance guy, there are a lot of things happening, okay, and everything is associated with a relative cost. So this is nothing but design cost, okay। This is how you relate the concepts, okay, by reverse engineering them. So everything, a lot of people are working, everything is getting paid, right? Everybody is getting paid, plus the component cost and the ideation cost. So everything is relating to money here, cost, and our goal is to keep it minimum, okay, possible level, minimum possible level. Now design patterns for embedded system will study, okay। There are a lot of design patterns and, you know, best practices. We'll study a couple and then we'll revise. Okay, first pattern is state machine pattern, okay। स्टेट मशीन कभी स्टडी की है तुम लोगों ने? हेलो शुभम। शुभम, गुड मॉर्निंग। Shubham, you there?
Yes, sir.
Yeah, so I was asking if you have studied state machines. Do you know what state machine is? Ever studied in engineering? Yes or no? Simple answer.
Yes, sir, but not remembering.
Okay, no, I'm not gonna ask you questions right now. I'm just asking if you are familiar what is actually state machines. So the thing is, in embedded systems, we are now studying the design patterns, right? So this is the first design pattern, okay, state machine pattern. So it means that when we are studying the embedded system, it is always gonna have finite states, right? And state transition will happen, okay, from one state to other state. Suppose to give you an example, temperature sensor is reading the data, okay. Okay, this is a task, okay. Temperature sensor reading the data, okay. It can be represented in the form of a state, okay, state one. So and state transition can be represented like this, okay. There are different patterns in which we can represent the states, if you remember, okay, like this, and all the transitions are having different meanings, okay. So basically we define or we architect the state machine, okay. Okay, so okay, in your language I will say it's kind of a flow chart, okay, relatable to a flow chart of a system, okay, maybe something like this, okay,
Yes, sir.
kind of a flow chart, you remember now. So and state machine, okay, and after defining the state machine you code it, okay. So what we have done, we have we have a complex system with us, okay. We have studied the system and हमने फिर states define किए, ठीक है, मशीन में क्या क्या states है, then states के transitions देखे हमने from one state to another state, okay, and then we have coded it, okay. इसके बाद इसकी programming हुई है. So what happened is that system was complex, we divided it, okay, into states, and we represented the states in the code, okay. We represented the states in the code, and this made our coding and the entire system lot more easy and hassle free, okay. So this is why state machines are there. So the basically the problem here is that embedded systems are often having finite states, and transitions between those states, and managing these transitions can become complex, as a system grows further, okay. And state machine is basically the solution, okay. We use state machine to model the system's behavior, okay. Each system represents a specific mode of operation, okay, and the state transitions occur based on the input or the events, okay. So here systems with distinct operating modes like power on, like standby, like active mode, protocol handling and control systems. This is where this can be used. Okay, suppose a system is complex and having distinct operating modes like power on, standby mode, like active modes. Okay, then protocol handling and control systems, such uh, at such places this can be used. So what benefit does it give us? Okay, it gives us a clear structure, yeah, and clear structure and organization. Okay, it's easier to debug and test the transitions. So that's what it is. Okay, it is easy to debug and test the transition. अगर कल को जाके कुछ I'm not able to achieve something in my system, I'm not able to do anything in my system. Okay, I can always go back to my state machine ka diagram and I can see this state is going wrong and I know where to repair. Okay, what to repair if something is going wrong. Okay, this is easy, debug and test the state transitions. Okay, plus in addition to that, what happens is a typical implementation uses an enum to represent the states. Okay, with with a switch case or a function pointer approach, for state transitions. So how the state implementation is done using basically an enum for states, with a switch case or a function for pointer approaches, function pointer approaches to state, represent the transition in a state. So this is how it is implemented basically. So this is our first design pattern. Okay, uh, and basically one of the standard practice. Okay, then we have an observer pattern. This was a state machine pattern. Then we have observer pattern. What is observer pattern? So multiple component need to be notifying when certain event occur, right? Like sensor or reading the interrupt. So solution, I mean, what is the problem in this then? Suppose uh, again same example, suppose temperature sensor is getting detected. Okay, then other components of the system also needs to be notified about this change. Okay, this, 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 and this. Okay, and what it created lot of chaos in communication. Okay, strictly bounded parameter. Okay, strictly bounding has happened here. Okay, there is connection. Okay, there is connection from one entity to other for communication. But is this seamless? No, this is not a seamless communication. It is a very complex communication. Multiple components need to be notified when certain event occur. Okay, so event has occurred here and multiple components were in need of informing. So this is a problem to us. And what is observer pattern then? Observer pattern is then kind of subscriber model. Okay. Suppose you want to get notified on something, you says, hey, I want to get notified. So the observer pattern, what it does is decouples the event producer, okay, subject from the event consumer, which are observers. Okay, so event producer is the subject. Event produce means temperature detect हो रहा है, that is an event producer. Okay, and rest of them are consumers, means observers. Okay, subject and observers. So the subject notifies the observer when changes occur. Okay, when the produce change is produced, the consumers are always notified on that. Okay, so we are building the observer pattern for that. So what happens, these are the observers or these are the consumers, right? So what they'll say, they will subscribe to this change. Okay, if this particular task or this particular resource is in need of knowing this change occurring, then it will subscribe for that news. Okay, it will subscribe for that change, and then it will know if once the change occurs, it will send it, it will broadcast it across its subscribers. Okay, and then it receives the message. So this is how it has made easy with observer pattern subscriber based model. Okay, so it is used where like event driven systems are there, interrupt handling is there, sensor data connection is there. So interrupt handling, then a lot of sensor driven systems. This is where it is used most, the observer pattern. Okay, the observer pattern actually has done decoupling of all the links that have shown you earlier. Okay, so those links have been broken because of this. Okay, and thus the complexity got reduced. Now I want to point here out that this is all being done for an embedded system, right? An embedded system is always a resource constrained system. Okay, resource constraints are always there. Okay, why? Because it is a tiny small system, okay, with limited resources. Okay, we can't just go and like, okay, do this, do that. No, we can't do this in embedded system. In general purpose computer, that is still fine, but not fine in embedded system. Okay, and that's why we are in need to design all such things, right? Observer pattern is also doing the same. Okay, it is decoupling everything. Okay, there was a tight coupling before. Okay, in order to just notify about the change being made, but with the observer pattern, what happened is that this chain got broken, this decoupling happened, means extra space. Okay, the burden of complication got lifted from the embedded system, and this is the entire goal of our design. Okay, रिसोर्स कंस्ट्रेंट सिस्टम है तो उसको ऐसे ही डिजाइन करो. Okay, so what it basically does to our system is, okay, it reduces the tight coupling between the system components. Okay, it facilitates the scalability. Okay, by adding more observers without modifying the subject. Okay, subject में कोई changes नहीं हो रहे. We, if the more observers got added, then those can also subscribe and get to know about the changes happening. This is one thing. Okay, then implementation, okay, typically involves defining an observer interface with concrete observers that subscribe to the event or the notification. So you know what is interface, right?
Yes, sir.
Yeah, so the implementation of this is done with the help of interfaces. Okay, so interface has to be implemented. If this has to be implemented, and an observer can subscribe to the event subject. Okay, which means the event that is happening, and this is how it is done. Then the next pattern we have in place is singleton pattern. Okay, okay, a resource such as communication port, a sensor interface, or a memory pool, okay, should be accessed by only one instance across the system. Okay, by only one instance across the system. Okay, any resource should be accessed only by one instance across the system. It means, could be that You create classes in programming, right? Then you create instance of that class and then you call that class, right? Using that instance. Do you remember that?
Yes, sir.
So singleton pattern is nothing but the same, okay? So some resource, okay? There's some resource, then that resource should be called only using single instance globally, okay? So this is what singleton pattern means basically. So we using the singleton pattern to ensure that the class has only one instance and provide the global point of access to it. Okay. So it is used in hardware drivers, communication channels and logger system, right? Where logs are there, huge logs are there. Okay. And its advantages are to ensure the single point of access of shared resource. Okay. It also reduces the overhead from creating multiple instances. Definitely ensures the I mean how it is implemented is, and we are ensuring what the class a constructor is private, okay, and provide the static method to access the single instance. Okay, you must be familiar with these terms, right? Constructor, and the private, and provide the static method maybe to access the single instance. This is how it is implemented. Okay.
Yes, sir.
Two main points. Okay, class ka constructor is private. Okay, and we have a static method. Okay, मतलब ज़्यादा कॉम्प्लिकेट नहीं करूंगा मैं. सिंगलटन पैटर्न इज नथिंग बट एक ही ये चाहिए, इंस्टेंस चाहिए, सिंगल इंस्टेंस ऑफ अ क्लास. ओके, ग्लोबली to call that class maybe, or to call that resource, to access that resource, create a single instance. Okay, it will reduce, it will cut down on the overall overheads of creating multiple instances, and it will give less load to system basically. Okay, so let's stop for the day with this. Tomorrow we'll start with command patterns, and there are strategy patterns, and then we start with the best practices. Okay,
Yes, sir.
let me stop recording also.